All right, hello everyone. Now let's take a look at some compound interest problems. All right, so compound interest is one that you're probably a bit more familiar with in terms of that being, this is what banks actually use. Instead of getting the interest as a linear amount based directly off the principal of the amount that's put in, like some percentage of the amount that you put in, instead, you get a percentage of everything that's in the account, including other interest. So, for example, if you put $100 into the account and you get 5% interest, instead of getting $5 per year based off the original 100, you would get 5% of the current total. So you would get first $5 for the first year, but then you get 5% of 105 instead of 100. And those sorts of interest rates will lead to exponential growth. And we'll talk about the effects of all of that in this particular scenario. But a lot of you are already familiar with compound interest from previous work, so we're not going to go too far into it. But what we can do here is we can take a look at this from a bit more of an applied standpoint, more so perhaps than some other cases. I think in pre-calc, one of the biggest uses that you use of it is, solving special types of equations with logarithms and other things, just as solving practice. But here, our focus in this unit is going to be the application of it and what the results mean, more so than the solving of it. Case in point, I'd like to tell you a story about one of the unsung heroes of the American Revolutionary War. Um, his name was Haim Solomon. Um, he's a Jewish immigrant financier living in Pennsylvania. He comes from Poland. He's a Jewish immigrant um, living in Pennsylvania, and he has one really good skill: fundraising. He is a investor, so he's got a fortune of his own through various means, businesses, investments, and he's also very good at convincing people to use their money to do things. Um, he is all for American independence, so one of the big things that he does is he buys up all of the US government's French Treasury bonds in order to give the government liquid cash to pay troops, buy supplies, um, basically to, you know, win the war. There's a very good story involving him, actually, and another unsung hero um, that you don't hear enough about in terms of U.S. history class, and that's Robert Morris. Um, Maybe you're familiar with Robert Morris, especially if you're a basketball fan, because Robert Morris University fields a somewhat decent basketball team, and every so often has some upsets in the NCAA tournament. Um, but other than that, Robert Morris was a British American financier, and he too was coming up he was Washington's right hand man and came up with all kinds of um, accounting things, bookkeeping, fundraising, whatever. But behind him was this guy, Haim Solomon. And it said many, 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 many times in Robert Morris's personal diary, I sent for Haim Solomon. I sent for Haim Solomon. Because needed to get out of a bind, and the government needed money, the army needed money, General Washington needed money. So finally, in 1781, at the tail end of the Revolutionary War, Washington is preparing the logistics for the siege of Yorktown. This is going to be it. War is going to be over. Um, and he decides that he needs $20,000. Robert Morris is there and he says, no can do. We're tapped out. All of our money's gone. And anybody who has donated to our cause that we know of already has. So we got to make do with what we have. Washington says, hang on, get Solomon, bring him in. So he does. Solomon says, what can I do? And Washington says, hey, we need $20,000. Okay, boss, no big deal. And he goes and he quickly, as quick as he can, he hightails it back to Pennsylvania and um, whips up a bunch more fundraisers. Again, this guy is a master at raising money, and he gets the $20,000 um, in order to run the siege at Yorktown. And the rest, as you say, is history. Um, he loans the government $650,000. And this number here, $650,000, like this number, this is 18th century money, not current money. That's not adjusted for inflation. That's hard earned colonial cash right there. So that has a value adjusted for inflation. This has a value of about 16 million nowadays, something like that. It's huge, uh, but there is um, a big thing that happens. Congress has never paid him back. Now, obviously, the guy's dead, right? He dies in 1785, so not that long after the end of the Revolutionary War. So he does not really live long enough to see the Congress really kind of come into its own. At the time of his death, the French Treasury bonds that he holds are worth pennies on the dollar, simply because the nobody else would be willing to buy them um, because nobody trusts that they would be repaid by either France or by the U.S. government. Um, so the government's credit rating has no credit rating at this point. It's basically the same as a 17-year-old trying to buy its first car. Um, so they have no credit score, no rating. Um, so Haim Solomon is essentially broke. Um, now the family, but Haim himself, selfless man that he was, never ever ever asks for repayment, ever. And it was really kind of selfless of him to do that. However, he did um, take out official documents as to these treasury bonds. So even though he never intended to be repaid or wants to be repaid, um, he did sign documents with official interest rates and repayment terms and all of that. Absolutely, he did. Even though he also has to agree for the repayments to start, and he told Washington, "No, I don't want you to ever start repaying me." His family, though, on the other hand, has thought differently. Thought that maybe he should be compensated, and his family should be compensated for the work that he did, regardless of his wishes. Thought that's only fair, which they have a point. So it's come up a few times in Congress to try to give something back to the family. The last time I believe was 1925, where an idea was floated to try to appropriate some money to pay the descendants of Haim Solomon. But it's always been, it's never really been passed through Congress. And then at the same time, the family has also requested more than what Congress was willing to give. So the family's never really accepted any terms of Congress anyway. I believe the last amount that was floated was somewhere about $1 to $2 million to repay him. And the family said no, um, simply because he's owed quite a bit more than that, actually, due to interest. So what is known, though, is those actual treasury bonds themselves. Here's the thing. Those are legal documents, and so there is a legal loan that is out there. Those documents have been lost since the 1840s. Um, if those documents ever turn up, then the US government would have no choice but to repay all of it. Um, including any repayment, the way that it's stated as in terms of repayment terms. Um, so exactly how much would that be? We're about to find out. So what the government has been trying to do was to see if they could find a way to satisfy this and essentially pay the family off and get them to agree to that the loan is satisfied without the actual documents. Therefore, the government can pay them a lot less. Because how much do they actually owe the family? Let's find out. So the loan's value, like it may have an interest rate, but we don't know what that is because we don't have the documents. So let's say that the loan's value parallels average GDP growth of 3.18%. Uh, Over the course of the last 2 centuries, that's how much the economy has grown on average per year. Um, so in terms of like GDP stands for gross domestic product, and is also a measure of like, how much goods and services we put out, how much money is in the economy, et cetera, et cetera. So let's say that because the economy is getting bigger, we can assume that like inflation is taking over. So this is like kind of a measure of economic growth, inflation, all rolled into one. Okay. So because of this, we're not going to worry about inflation at all. So it grows by 3.18%, but that's every year. And that's any money that goes in as a result of this also gets interest. As a result, we're going to need compound interest formula. So here's the formula for that. Um, as we know, we're going to go from linear to exponential, and this is the formula. So it's pretty similar with a couple exceptions. The t is now an exponent instead of a multiplicative term. And then you have this n. What n represents is the number of periods per year in which interest is calculated. Um, so just as kind of a rough, just kind of a quick explanation of n again for those of you that don't quite remember. So n, like if you were to take a bank account, and let's say in a bank account you get 5% per year, right? So what could happen is you could have the balance in your account multiplied by 1.05, um, say every December 31st. You get 5% every year. Um, the problem with that, though, is if you did it once per year, first off, the bank would then have to pay everybody once per year, and maybe they don't have the money to do that up front, like December 31st. Oh, put all this money into everybody's account. The other thing is from the personal standpoint, if this is true, what would you do? Well, you would take a ton of money that and you would throw it if you know that you're going to get paid interest every December 31st. You're going to take every penny you have and throw it in that account on December 30th, get that interest, and then take the money right back out again on January 1st, 2nd, so that you can use it elsewhere. So that's what everyone would do. So instead of getting paid, say, 5% once per year, what if you got paid 5/12 of a percent of interest per month? That still adds up to 5% because you'd be getting that 12 times. Um, so you could do that per month. And then every month, instead of every year, you get just a smaller amount. So it takes the interest and it breaks it up. And it makes it easier for the bank to pay you. And it makes the amount in your account more consistent too. And you don't have to really worry about it. What banks actually do is they do this on a daily basis, 5/365% per day. That's really the way they do it. And so they give you the interest every day. So it's pennies, like fractions of pennies, that they give everybody every day. And that's actually the easiest way um, to do it. And so now what we can do is we can look at this problem. So for the moment, though, we're going to ignore n. We're going to assume that because we're dealing with gross GDP, yeah, I know economy shrinks and grows every day. Um, let's assume, though, for the moment, it's just once, just because we think about it once per year, just to make the problem easy. Okay, so let's figure it out. Okay, um, so we have F, P, R, N, and T. So we're going to say N is 1. We're going to say R 0.0318. Um, P, $650,000. And T, well, let's see, 1780, let's see, 1781 is probably the last time that he loaned out the money for the end of the war to 2021. Well, that's a total of 240 years. So holy moly, 240 years. All right. So 650,000 times 1 plus. Now the interest rate, 0.0318. We're not going to worry about n, and we'll just raise it to the 240 power. Okay? So we're going to take 1.0318, and we're going to do exponent to 40, and then we are going to multiply that by 650. 190,800,492. And then there's some decimals after that, but at this point, who cares about cents? Look at this number. This number is equal to $1.2 billion. If those documents ever come due, the government is going to have to pay this family $1.2 billion. Wowzers. Now here's something else I'd like to point out to you. This is the power of compound interest. When money sits for a long time, the longer it sits, the more it generates. And 3% isn't that much. But holy moly, $650,000 turned into over $1 billion. It took 240 years to do it, so not something you'd see in your lifetime, certainly. Um, but it's even still respectable in a lifetime. But I'd like you to point something out. Again, the power of interest. This is the fourth or fifth time I've now done this problem and done this situation in my classes. The very first time I did this was we looked at the problem a few years ago when the exponent was only 235. So I want you to look at this right here. The very first time I wrote these notes, we had an exponent of 235. Look at the total, $1.02 billion for 235 years. When we did 240 years, it's 1.2 billion. Guess what? That's 180 million, 170, $180 million in 5 years. How bonkers is that? Look at the difference. If money sits that long, just the amount of interest is in 5 years, $170 million in just interest, just generating on its own. You should leave this for your leave a few dollars for your great grandkids, huh? Okay. So that's kind of an introduction into how this formula works. So in this particular case, we didn't have to solve anything. Again, we just plugged everything in. We had to find the future value. So we just plugged everything in, did the math, done, right? But remember that just like the simpler formula, we can solve for anything in this formula too. So let's do a few example problems, just solving for various letters here. So other than F, you could certainly solve for P. You can solve for r, and you can solve for t. Um, Solving for n can't really be done algebraically. With having it both as a fraction and as an exponent, that would be a tough thing to do. Okay, so one thing before we get to that though, as a few of you did point out in class, um, when you have an interest rate, 7%, like you can get that 7% once a year. But remember I said that sometimes you could break it up, and most of the time in the bank, it breaks it up into monthly or even daily. And that gives you more money. So consider a $2,000 investment at 7% for 6 years. If you just do the 7% once a year, so you do it 6 times, once per year, you're making exactly 7% every year. And so you're going to get a total at the end of $3,001.46. You can trust me on that. Do the math if you want. Um, P is 2,000, R is 0.07, N is 1, and T is 6. What if you change to N is 12? Then it becomes 7 over 12% interest every month for 72 months. The amount goes up to 3040.21. Daily, if N is 365, you get this amount. And the reason why this is happening is because with the interest broken up throughout the year, some of the money you get some interest in the account um, is getting like double dipped, triple dipped into this. So like the January amount of the 7 over 12 will then have interest applied through it all the rest of that year instead of only at the end of the year. So you are going to make a tad bit more money doing that. Not much, um, as you can see. Once you hit daily, it really doesn't pay to do it anymore. So that's why banks do it daily. It's easy for them to do, and they don't have to worry about giving people money every hour or even every second. Okay, so that's the effect of n. Essentially, um, the values of n that you're going to see um, in this class. You'll see 1 for yearly. Um, not as often, but you will. The ones you're most likely to see are 4 for quarterly, 12 for monthly, and then 365 for daily. Those are the ones you're most likely to see. There's some other uncommon ones, weekly, bi-weekly, where bi-weekly would be n would be 26. And there's some other ones like that, but we're not going to really do those too much. Okay, um, we'll skip that for now. We don't need to worry about annual percentage yield. Let's not worry about that. Let's just go straight to some problems. Okay, if $2,500 is invested with interest compounded quarterly, there's a quarterly problem. What annual interest is needed to be worth $3,000 in 15 months? Okay, so here's my formula. F equals P1 plus R over N to the NT. Okay. Okay, so what do we have? $2,500 is invested, so that must be P. With interest compounded quarterly, so quarterly means N is 4. What annual interest is needed? So we're going to solve for R. Is needed for the investment to be worth $3,000 in 15 months. Okay, so 15 months is 1.25 years. Again, you could do 15 over 12 if you'd like, but here it's a nice easy number to work with, 1.25. Okay, all we have to do is plug it in. 3,000 equals 2,500 times 1 plus R over 4 to the 4 times 1.25. Okay, folks, this process will not change from problem to problem. We're going to write the numbers out, we plug them in, but what will change is you're going to have to solve the equation. And how you solve that equation will differ from problem to problem. Again, think about all your opposite operations. You might need to divide, you might need to multiply, you might need to use, um, you know, exponents, you might need to use logarithms, whatever. Okay, let's start by dividing by 2,500. So 3,000 divided by 2,500 is going to be actually 6 divided by 5, so 1.2. Okay, so let me just double check that. So 3,000 divided by 2,500, yep, 1.2. Okay, now 4 times 1.25, you might know that is 5, which makes sense because 15 months is 5 quarters. That's, 3 months is a quarter, so that's going to be 5 quarters. So 5 interest-bearing periods. Okay, so now we have to solve for r. How do we solve for r when we have an exponent? Remember that just like our problems in the first unit, uh, we use an exponent of 1/5. This will create decimals. That's okay. So we're going to do 1.2 to the 1/5 power. Exponent 0.2. Okay, and that's going to give you a value of 1.037. So remember what I said before, we want to try to keep this as close as possible. So we're going to do, I'm going to write out the full 8 decimal places for this. 1.0, 1.03, see, so 1.0371, 3729 equals 1 plus r over 4. Okay, and now all we have to do is subtract and then multiply. So subtract the 1. So 0.03713729 equals 1, sorry, no, not r, just r over 4. And then we multiply both sides by 4. So subtract 1, multiply by 4, and I get 0.14855. So R is 14.85%. Okay. So again, R will always be represented at the end as a percentage. Even though the answer you get is a decimal, always multiply by 100 to turn into a percentage. So $3,000 in 15 months. Now that actually makes sense because that's going to be that is 20% more than 2,500. So that number does make sense. That's probably a bit more of an interest rate than we really can get, but that's okay. Okay, here's another problem that we'll do. So the other kind of problem that I think that would be important um, for you to see is how to do one that involves a logarithm. Okay, so the other kind of equation that's pretty important is one like this. The key to read here. $1,600 is deposited into an account earning 6% compounded monthly. How long would it take to have $2,500? The key words in this problem, how long? When you see those words, how long or how much time, you're solving for t. And when you're solving for t, that means you are going to need logarithms because t is in the exponent. So let's write it out. F, P, R, and T. CF there. All right. So $1,600 is deposited into an account, earning 6%, compounded monthly. How long would it take for the account to have 2,500? Okay, 2,500 equals 1,600 times 1 plus 0.06 over 12 to the 12t power. Hey, doesn't this look like some of the equations that we did in the very first section of this chapter? Okay. So let's start by dividing. So 2,500 divided by 1,600. 1.5625 equals. Now, let's figure this out. 0.06 divided by 12, well, 60 divided by 12 is 5. So if I were to do this, I'm going to get divide by 6 to get 0.01, then by 2 to get 0.005. So 1.005 to the 12t power. Okay. So now what? Again, at this point, we need to get that t out of the exponent. So this is where we use a logarithm. So remember our work on logarithms says that to bring that t down, and so log of the base. So if you have, sorry, let me write this a bit better here. Um, if you have an expression that's like this, b to the x equals y, then log of y divided by log of b equals x. So in other words, the log of the constant term, the non-exponential term, divided by the base of the exponent equals the exponential term. So what you're going to do here is you're going to do log 1.5625 divided by 1.005 log 1.005. Let's do that math. So again, I've got my nice calculator here. So we'll do I have a log button? I do. I have, so I can do, let's clear. Log, oops, oh right. In this calculator, I have to hit the log button second. Sometimes you have to hit the log button second. If you're using a calculator, log button comes first. 5625, log of that, divided by 1.005, log equals 89.48. So again, we'll do a bunch of decimal places here. So 89.4803. 78.59. And that's going to equal 12t. Because now that is equal to the exponential term. And then all we have to do is divide by 12. And that's going to give me about 7.46 years. 7.4567. Okay, let's scoot this down. Okay, we'll scoot that down. Okay, so now that we have this, we can simply divide everything by 12, and so we get 7.4567 years. Okay, so we have a little over 7.5 years in which to pay this, or 7.5 years not to pay it, but to earn that much money. So that's kind of interesting to be able to solve for problems like this. Um, yeah, so really all the problems kind of work out much the same way. So we'll probably do more examples a bit. I don't want to make this video too long, but I figured I'd give you one example of each of those that we can do. Um, if you want to try this, you can give it a shot. Maybe try it again with daily compounding and see if you get a little bit of a different result here. You can do the same math, see if you can do it. You're going to get a value that's just ever so slightly less than this. And you may think like, oh, isn't it just going to be divided by 365 at the end? But don't forget that the log base is going to differ too. So you're actually going to get a value that's just slightly lower than 7.54. I don't know the exact number off the top of my head, um, but it should be very slightly lower than that, like maybe like closer to 7.5. Um, so try to see if you can do that. Okay. Um, other than that, um, take a look here. It's a good example to kind of follow. All right, folks. Have a lovely evening, and I will see you in class.